My name is Lucian Constantin and I'm a former doctoral student at the University of Bristol. This is a presentation that is based on my PhD thesis titled Experimental and Numerical Investigations in Wing Loads Alleviation using Fuel Sloshing. This work was conducted as part of the Airbus-led project called Sloshing Wing Dynamics, abbreviated SLOAD, in partnership with the institutions shown here. First of all, some background and motivation for my research. Substantial quantities of fuel are stored inside the wing integral fuel tanks, oftentimes with fuel mass comparable with the structural wing mass. Aircraft manufactured in Europe must follow certain certification specifications and acceptable means of compliance, and large passenger aircraft fall under the CS-25 specifications. When it comes to indications for design calculations, it is specified that 1.5% critical damping ratio should be considered for all flexible modes, and that this value can be increased if justification is given. This is where the idea of obtaining a better understanding of vertical fuel sloshing comes into play, and this is also where the industrial interest lies, as emphasized by the Airbus-led SLOAD project. There is industrial interest in quantifying the energy dissipation due to vertical sloshing, as well as trying to exploit it in order to increase the effective damping above the 1.5%. As can be seen in this video, the main vibration modes regularly excited by wind gusts are out-of-plane bending motions, which can also be studied via simplified systems, as underneath here. These observations lead us precisely to where liquid sloshing would fit in the larger aeroelastic picture. Classically, aeroelasticity is a field of study placed at the intersection of three more fundamental interactions: elastic phenomena, inertial, and aerodynamic forces. The sloshing fuel is thus not modeled at all during the aeroelastic design phase of the aircraft. There is this fourth component, which is not connected directly with the aerodynamic forces, but it does interact with them via the interaction with the wing structure. It is thought that the inclusion of fuel sloshing during the design phase may lead to less conservative designs via the increased damping due to vertical sloshing. The reason it is not included right now is that it is rather poorly understood and modeled. Having established the background, let us turn to my thesis aim and objectives. The aim is to analyze the nonlinear dynamic interaction between aircraft wing structures and the fuel inside them, with a focus on discrete gust-type excitations. 5 specific objectives were set at the beginning. The first 2 objectives are set for the understanding of the fundamental mechanisms that cause the sloshing-induced damping, as well as for the initial quantification of the sloshing-induced effects in single degree of freedom vertically vibrating systems. Based on the fundamental data that was gathered for objectives 1 and 2, I plan to develop numerical models in order to offer further insight, and also because they are highly relevant to current academic and industrial research. My focus was on equivalent mechanical models developed for fast evaluation of large amplitude vertical sloshing regimes, to be perhaps also included in control systems. With a solid fundamental understanding of the vertical violent sloshing-induced damping effects, objective number 4 imposes the quantification of these effects on a scaled wing research prototype. The aim was to develop such a wing sloshing platform, instrument it and test it in order to evaluate major influencing parameters that I have noticed in previous experiments. Finally, objective 5 seeks to synthesize the sloshing-induced damping effects based on what were quantifiably the most important influencing parameters, such as vertical acceleration and filling level. I use synthesis here in the sense of the combination of all components and elements in order to form a connected whole, namely linking the phenomena observed by investigating the single degree of freedom and multi-degree of freedom systems and the numerical models. In order to achieve these aims and objectives, I structured my work as shown here. It is roughly divided in 2 parts, with the first 5 chapters involving relatively fundamental research and analysis, and the final chapter presenting an applied study. Chapter 3 is concerned with the experimental analysis of a transient single degree of freedom system, Chapter 4 with the analysis of several single degree of freedom harmonically excited systems, and Chapter 5 with the development of equivalent mechanical models based on these experiments. Finally, Chapter 6 considers the design and testing of a multi-degree of freedom scaled wing research prototype, applying all of the previously learned lessons to this more realistic test platform in order to achieve objectives 4 and 5. As As also stated before, the main direction of sloshing in bending wing tanks is vertical. Let us thus start with the single degree of freedom vertical sloshing experimental studies, which are presented in chapter 3 in my thesis. The design of this study implements a vertically vibrating tank which is deformed to an initial deflection and then released into free decaying vibrations. The free vibrations of the system are then analyzed. Conceptually, such a vertically vibrating single degree of freedom sloshing system could have an elastic and a damping element as presented on the left-hand side. A low value of dry structure damping is desired in order to improve the sensitivity of the system to sloshing-induced damping effects. The experimental implementation studied in this research is presented on the right-hand side. Two 1 mm thickness steel strips are used as the elastic element, their T-shaped configuration allowing for substantial linear deflections of the attached tank of up to 14 times the strip thickness. It was shown that this configuration limits the tank motion to the vertical direction. Alternative configurations are possible too, like the approach of our colleagues at the Polytechnic University of Madrid, where they used grounded springs instead of steel strips. The system vibrates at a dominant frequency of 10.05 Hz and the measured stiffness is 1100 newtons per meter. This leads to an equivalent mass of the system of approximately 276 grams. The dry structure damping ratio value was experimentally measured in the interval of 0.23 to 0.34%. A slight nonlinearity in damping can thus be observed, the damping increasing slightly at high accelerations. This, however, is inconsequential to the experiments presented here. This is a photo with the actual experiment where you can see the two elastic strips forming a T-joining point, the tank containing water and the loading mechanism consisting of a turnbuckle and a piece of thread allowing for step release initial conditions. Mass can be added here in order to maintain the total mass of the system constant when varying the tank filling level. An accelerometer is placed underneath the tank in order to measure its dynamic decaying response, and a high-speed camera was also used for further image analysis of the sloshing patterns. Let us now move to results. In this slide we can see a time history of the tank accelerations for the dry structure versus the 50% filling level case. First of all, there is a marked difference in the response amplitude between the two cases, adding water into the system reducing the tank amplitude quicker. The frequency of the system is kept constant at 10.05 Hz, regardless of the filling level by using the added mass. The energy dissipation rate was observed to be exponential, typical of viscous-like damping, and having different values at different times. This leads to the emergence of three different damping regions. Although harder to notice on a linear scale, it is oftentimes easier to observe damping behavior on a logarithmic scale. In this example, only the envelope of the acceleration signals for the 50% filling level and dry cases are represented on a logarithmic scale. If the envelope varies linearly on a log scale, the viscous damping ratio can be measured from the slope of the curve. It is thus easier to observe the three damping regions corresponding here to the three different linear regions. First of all, it's important to note the very low damping in the dry structure, seen by the slope of the black curve in this graph. Also, you can see here the very small nonlinearity in damping I mentioned earlier, and how it really has no effect on the larger picture. A correlation has been observed between the different damping zones and the physical behavior of the fluid, as seen here and categorized as region R1 with turbulent vertical fluid motion, region R2 with symmetric lateral sloshing motion, and region R3 with small fluid activity following the tank base motion. It is worth taking a closer look at the fluid's behavior in these three damping regimes. In the first region, corresponding to the highest levels of damping, the fluid absorbs energy out of the primary system via repeated impacts with the bottom and ceiling of the tank, as you can see in this video. This regime is thus characterized by violent, turbulent vertical motion of the liquid. A damping ratio of approximately 1.76% was obtained for this particular experiment, the tank's peak amplitude being reduced from 14 mm to approximately 3 mm in little more than 10 oscillations. The second region of damping occurs immediately after the peak acceleration level in the system reaches 1 g, and the turbulent vertical motion of the fluid is stopped. R2 is characterized by fluid sloshing on its first symmetric sloshing mode, in this case, for which standing waves with symmetric motion is typical. The dissipation mechanism is related to the transfer of energy from the vibrating primary system to the fluid sloshing on one of its modes. The damping ratio obtained is lower than what we've seen in R1 at 0.87%, and the peak amplitude of the tank is reduced further in R2 from 3 mm to approximately 0.4 mm in this case. Substantial levels of damping are thus associated with R2 as well. Also notable is the duration of this regime, lasting for approximately 5 times more cycles than R1. The third region of damping is relatively uneventful. At the end of R2, the motion of the system is greatly reduced, and consequently the fluid stops sloshing as well. The value of the R3 damping ratio is the same as the dry structure damping at 0.22%. Two different sets of experiments were performed to systematically investigate the effect on the sloshing behavior when varying the filling level in the tank, and also when increasing the initial deformation before the step release. The aim of the first set of tests on the left-hand side was to explore the effect of the different tank filling levels on the transient response whilst maintaining the same initial deformation. The beam was pulled downwards by the cord attached to the turnbuckle so that an accurate and repeatable amount of deflection, 14 mm in all cases considered here, was possible. Filling levels between 0 and 100% were considered. The second set of tests considered the effect of changing the initial displacement between 1 mm and 14 mm, and hence the maximum acceleration experienced, which is up to 7 Gs, before the system was released into free vibrations. These tests were repeated for 3 different water filling levels of 30, 50 and 70%. A summary of all the damping trends obtained when varying the filling level is presented in this figure, which shows the damping ratio estimated in each of the 3 regions and for each filling level. The dry structure damping values, essentially equal to the damping in R3, are also shown using the red lines. All values shown here were identified using an automated procedure for damping region delineation and quantification. The sloshing-induced damping effect in the violent vertical regime R1 is found to be maximized at 50% filling level, consistent with other findings too. The damping in the second region R2 is found to be substantially smaller, and it does not follow the same clear trend with the filling level. Considering the correlation between the fluid sloshing mode and the measured damping ratio, inevitable variations in the sloshing motion lead to variations in the measured R2 damping ratio. Moreover, the sloshing frequency of the fluid varies as a function of filling level, further influencing the damping ratio in this region. Typical R2 results are presented here, and supplementary focus is placed on this regime in the harmonic excitation studies to follow. The R3 damping is found to be very low overall and close to the underlying damping of the dry structure. This finding is consistent with the qualitative behavior of the fluid observed in the previous slides, namely that in the region R3 the fluid contributes very little to the system's energy dissipation. The effect of excitation level or maximum acceleration level on sloshing-induced damping is assessed by varying the peak acceleration via different initial deflections for 3 different filling levels. The main result is shown in this figure, where damping in the first region is shown as function of the maximum acceleration amplitude A0 over G. The damping trends for the 30, 50 and 70% fill level cases are compared. As in the previous slide, it can be seen that the R1 damping levels for the 30 and 70% filling levels are similar. A piecewise linear function was fitted over the R1 damping versus maximum acceleration data. The 2 linear regions are thus established, and similar slopes are obtained for all 3 filling levels, with the line corresponding to the higher excitation levels having a considerably lower slope compared to that at a lower excitation. The damping ratio thus only increases slightly after the acceleration threshold is reached, mainly due to the dry structure damping nonlinearity. It follows that only slightly more energy is absorbed in the R1 region as the maximum acceleration level goes past the approximately 3.3 G threshold. The second experimental campaign is focused on the harmonic excitation of rectangular partially filled tanks in the vertical direction, and it was done in two parts using different actuation techniques. We have already seen how the sloshing system behaves under transient large amplitude conditions, and we now shift focus to steady-state behavior with well-controlled sinusoidal motion, thus constant amplitude and frequency of excitation. The specific aims of this study are to show and explain the dissipation trends at large amplitudes and different frequencies of excitation, and these are the types of regimes that are considered here. The second aim is to gather supplementary experimental data for numerical model developments and calibration. The main challenge in this type of study is achieving large vertical amplitudes whilst maintaining the tank dimensions large enough such that the effects that we are interested in are still dominant. So for example, we will have no significant surface tension effects. The setup thus consists of a rectangular tank, 100 by 30 by 50 millimeters, partially filled with liquid, placed on top of a large amplitude shaker with a force sensor in between. An accelerometer is also placed on the tank in order to collect the tank acceleration, velocity, and displacement information. Different amplitudes and frequencies of excitation are considered according to a pre-established test matrix that you can see here with the details presented in this table. Each amplitude and frequency combination was studied independently, with each test running for a sufficiently high number of cycles in order to achieve steady-state behavior and to have a representative number of tank cycles to analyze. In order to characterize the sloshing-induced damping effects, a damping metric is needed for the sinusoidal excitation case. I show here both the dimensional energy dissipation per cycle, measured based on the tank force displacement hysteresis cycles, as well as the form normalized to liquid mass, frequency, and amplitude of excitation, E sub c. An equivalence relationship can be established between the non-dimensional energy dissipation under sinusoidal excitation, EC, and an equivalent viscous damping ratio, zeta, as you can see on the right-hand side. The results for the three frequencies of excitation are shown here, with amplitudes of up to 1.2 tank heights. As in the transient experiments, the same sloshing regimes can be observed. In this context, the R2 regime is well described classically, with the emerging sloshing standing waves that depend on frequency being well understood. A combined R2 and R1 regime appears due to increased resolution in amplitude, where a non-linear standing sloshing wave appears with impact with the tank ceiling. And finally, the now familiar R1 violent regime at large amplitudes. It is interesting to note in non-dimensional form that all three curves overlap, as can be seen on the right-hand side. There is, in fact, only one parabolic function that seems to be describing the large amplitude damping response, which can be explained and will be explained later based on kinematics reasoning, as we will soon see. High-speed camera was also used, and based on the captured footage, I developed an algorithm for the statistical analysis of sloshing patterns. Here you can see some examples of persistent sloshing trends over multiple sloshing cycles, and for each Froude number or tank amplitude, there is characteristic behavior that drives the damping response. The velocity field of the liquid relative to the tank can also be obtained using optical flow, shown here with the black arrows and the streamlines in red curves. These are some instances of the sloshing pattern at one set amplitude of excitation. Together with the sloshing force information, which can be derived from the force sensor, and the information from the accelerometer, there is complete kinematic and dynamic information that is available experimentally for detailed analysis. The power of this type of analysis resides in the ability to describe the sloshing hysteresis cycle experimentally in great detail. Here we see an example of the hysteresis cycle, namely sloshing force versus tank amplitude normalized to tank height, with the four main points of interest, A to D. On the right-hand side, the sloshing force is represented as a function of time, together with the mean vertical bulk speed of the liquid that was obtained from the optical flow technique. At large amplitudes of excitation, there are also two sloshing force peaks inside each tank cycle, points B and D, which correspond to the bulk liquid impacting the bottom and top of the tank. What is less obvious and intuitive are the second set of peaks, A and C. What I found is that the secondary peaks appear at very large amplitudes of excitation because of liquid rebound from tank bottom or top, after which the oscillating tank impacts the liquid a second time. This phenomenon is easier to see at large amplitudes by looking at the liquid mean relative vertical velocity, the orange curve on the right-hand side. Following the rebound of the liquid, as the tank goes upwards, the liquid starts to push against the bottom of the tank the second time, creating a new interactional activity against the upwards motion of the tank. This effect causes the average liquid bulk velocity, Vzm, to be constant between points B and C, and subsequently the recovered sloshing force features a second peak at point C. The interactional mechanism is similar for the impact with the top of the tank, and the argument is the same between points D and A. The second heat effect is less noticeable, though, in the sealing interaction case, as it is not aided by the gravitational acceleration, and the net inertial effect of the liquid against the tank is less evident. This effect is particularly important for the development of equivalent mechanical models, as any such model will need to replicate these effects in order to represent correctly the liquid sloshing action in such R1 regimes. Continuing the analysis of the sloshing hysteresis cycle, here we see a comparison of the cycles at various amplitudes of excitation. There is the main hysteresis dissipative loop that forms, and then a secondary positive energy contributing subloop that starts to form at very large amplitudes. This happens because the phasing between the tank velocity and sloshing force changes, with the liquid hitting the bottom of the tank, aided by gravity, before the tank reaches its minimum stroke position. Under such conditions, the sloshing force does not act in quadrature to the tank velocity anymore, and, instead of having a dissipative effect, it rather adds energy back into the system. In turn, the development of these secondary hysteresis subloops explains why the dimensional energy dissipation trends deviate from the linear increasing trend at large amplitudes, with a decreasing parabolic trend being introduced for all frequencies of excitation. This wealth of experimental data that I have just presented can be further used for the development of numerical models. The use of numerical tools at different levels of fidelity, such as smooth particle hydrodynamics, SPH, volume of fluid, VOF, and equivalent mechanical models, EMMs, or reduced order models, ROMs, is well established in fuel sloshing and fuel structure interaction research. With the advent of high-performance computing, the use of detailed high-fidelity models for liquid sloshing problems is an attractive option. Alternatively, when in need of fast or large number of computations, such as for the optimum wing design, the use of low-fidelity models might be preferred. Equivalent mechanical models are based on simplified representations of the physics involved in the problem and provide a simpler formulation of the dynamics of the sloshing system. As this work is concerned primarily with a transversal out-of-plane dynamic interaction between a sloshing liquid and a tank, this situation leads to a problem formulation different in its nature compared to classically investigated sloshing systems where the liquid movement is lateral. In this work, I considered 3 different equivalent mechanical models, emphasizing their different features and limitations, together with supplementary explanations that are based on the model physics. The following numerical models are studied in this work with their key characteristics: analytic infinitely short impulse Ball model using the coefficient of restitution, numerical distributed interaction Ball model using linear and nonlinear spring dampers, analytic ballistic harmonic model for energy dissipation Ball tank trajectory analysis during violent sloshing. I will take each of them separately and present their main features and results. In the first approach, I modeled the bulk vertical motion of the liquid using a ball falling under gravity and interacting with the tank with a coefficient of restitution. The work on this model is motivated by the T-beam transient experiments discussed earlier, and the focus is placed on the R1 vertical violent motion. Based on experimentally observed behavior, namely on how the violent vertical liquid motion causes additional damping, this work uses a phenomenological EMM, where a simple linear spring damper mass oscillator is combined with a single free-flying ball contained and interacting with the upper and lower boundary of the oscillating system's mass. The spring damper mass part of the model represents the mechanical structure with the tank of mass m, uppercase M, stiffness K, and damping coefficient C. The ball in this model represents the fluid during its vertical R1 sloshing stage. While classically referred to as bouncing ball, in this case it behaves as a bouncing rigid body because it has a certain height, HL, depending on the water filling level, and represented in this figure as the rigid bars above and below the ball. This model was tuned over multiple filling levels and tested against multiple amplitudes of excitation. Here we see a comparison between the experimental data, the equivalent mechanical model results in black, and higher fidelity SPH simulations performed by my colleague Joe DeCourcy. The EMM gives good results in R1, the region with vertical impacts, and it does not model R2 at all. Thinking about what R2 means, remembering this type of low amplitude permanent wave motions, it indeed cannot be modeled by a vertical bouncing ball. In comparison, the higher fidelity SPH simulations model part of the R2 region. It is interesting to note the almost exponential envelope in R1, as shown experimentally and predicted with SPH, whilst the EMM indicates an evolution that deviates from this trend. On average, the damping ratio is the same in R1, but the different envelope shapes indicate a different dissipative mechanism. This slide shows a comparison of R1 damping with the experimental data across multiple filling levels, with a good agreement across all fills and a slight overestimation of damping at 10, 20, and 80 to 90% fills. At very low and very high filling levels, there are multiple ball bounces during one tank cycle, and thus the interactive mechanism differs more from the experimental observations. The vertical bars here indicate the envelope deviation from the exponential decay, meaning deviation from the viscous damping-like mechanism. As noted before, the deviations are larger in the bouncing ball case, indicative of the fact that the vertical dissipative mechanism is perhaps different in its nature than the coefficient of restitution mechanism. Finally, we can look at the variation of R1 damping with respect to the amplitude of excitation, horizontal axis here. Both sets of data predict the same damping saturation point, and the mean values are similar, indicative of good prediction capabilities across a large range of amplitudes of excitation. However good the agreement is, this model has certain shortcomings, namely the effect that the dissipative mechanism indicated by the coefficient of restitution approach seems to be different than the actual sloshing experimental prediction. This aspect is likely related to the fact that the sloshing interaction is distributed across the tank cycle, as we have seen, whilst this numerical model only considers discrete ball-tank interactions, many times only 2 of them per tank cycle, as shown here as maximum and minimum tank displacements. One model that addresses this aspect is the distributed interaction model, which I present next. The aim thus with this second model is to address these differences by investigating the possibility of using nonlinear spring damper connections between the bouncing ball and the tank, replicating at least certain aspects of the hysteresis cycles observed experimentally. There is a combination of bottom and top linear, third order and fifth order springs and dampers to model the ball-tank distributed interaction. The top and bottom elements can be different in order to make it easier to introduce possible asymmetries in both the bottom and ceiling interactions, even though they are kept the same in this work. Similarly to the previous model, this one was tuned by minimizing the difference between the experimental and numerical energy dissipation prediction. Jumping to results, this figure shows a comparison between the experimental and numerical results in terms of dissipative energy per cycle and sloshing forces. Note that there are no error bars associated with the numerical results in this case, as there is no time variation in the numerical hysteresis cycles and hence in the induced dissipative energy. The numerical results were computed using 2 different types of damping indicated by the values J. namely dependency of the damping force on the third and fifth power of velocity, according to the relationships shown here. The dissipative energy versus amplitude results on the left-hand side indicates a very good match between the model with the two different damping scenarios and the experimental results. For the third-order damping case, the energy values are slightly over-predicted for the lowest and highest amplitudes, showing a decreasing trend past the amplitude normalized to tank height of 0.3, with a lower slope than observed experimentally. The fifth-order damping case shows a closer match to the experimental results, with a similar high-amplitude trend and better low-amplitude prediction. According to the hysteresis cycles that are shown on the right-hand side, in the j=3 case, the shape of the hysteresis cycle is very similar to that observed experimentally, but rotated counterclockwise. The shape similarity is surprising, considering that the model parameter tuning was agnostic with respect to the shape of the hysteresis cycles, seeking to only minimize the numerical and experimental differences in dissipative energy on the left-hand side. The cycle tilt indicates additional mass or stiffness effects that are not completely modeled. Whilst this formulation has good potential for modeling the vertical damping effects, it still lacks in its modeling capability of the entire physical aspects of the problem. Notably, a direct comparison between this model, BB2, and the transient experimental case and BB1 is not meaningful, since model BB2 only works at the tuned frequency of 8.3 Hz. The dissipated energy was found to be over-predicted at higher frequencies of excitation and under-predicted at the lower end of the range, indicating that BB2 is suitable for modeling the hysteresis effects that are closer to the experimental measurements compared to BB1, but in its current form, it is still not capable of modeling the full complexity of the vertical sloshing effects. In light of these observations, the power of model BB2 resides rather mainly in indicating possible further paths towards more accurate modeling of the sloshing hysteresis cycle, which may lead in turn to a better agreement with the experimental data. The modeling approaches considered thus far were based on different formulations of the impact force between a ball and a tank, namely via a coefficient of restitution which causes a change in momentum, or combinations of springs and dampers which increase the complexity of the interaction. Earlier, however, it was shown that there is a similar large amplitude damping trend, at least inside a considerable frequency range, meaning that the non-dimensional energy dissipation curves overlap in the frequency range of 5.3 to 10.3 Hz. Moreover, similar damping trends were observed and modeled using the same tools in the field of particle impact damping. There is thus a strong indication that, at least at large amplitudes, the vertical sloshing system exhibits energy dissipation properties that transcend the liquid-specific qualities. The motivation of this numerical approach is to exploit kinematics-based reasoning for the fast and efficient computation of damping saturation limit and the large amplitude sloshing-induced damping. The hypothesis here is that at large Froude numbers, the kinematics of the problem, or the liquid tank impact velocity and the number of liquid tank roof or bottom impacts in one cycle, is determinant to the amount of the sloshing-induced dissipated energy. In order to test this hypothesis, the use of a kinematics-based ballistic harmonic model, called here BH model, is employed. The analysis presented here makes the assumption that the fluid may be treated as a single lumped mass following a ballistic path within a harmonically oscillating upper and lower wall, as indicated in this figure. The sinusoidal motion of two fixed distance walls is considered with a particle between them. There is no lateral motion, the fluid may not fragment, and no free surface modes are considered. Collisions are treated as inelastic, although it is clearly a significant simplification and one which can only finally be justified by the relative accuracy of the derived model. Kinematics-based reasoning of the dissipation trends is explored at multiple frequencies and amplitudes of excitation. This type of experimental data was shown earlier and is also used here for comparison against the BH model. These figures show the interpolated experimental sloshing energy surfaces and the corresponding experimental maximums EC, shown in red squared markers here. In the same figure, there is also shown the BH prediction for the maximum EC values, the gray curve, and the curve above which there are intersections with both ceiling and bottom of the tank, the dashed gray curve. As the acceleration of the tank increases, it imparts to the ball a high enough energy such that it hits both the ceiling as it goes up and the bottom of the tank as it comes back down, both within one single tank cycle. It can be seen that the experimental data generally follows closely this trend established by the BH model. The dissipative energy is maximized in the vicinity of the region where the kinematic conditions are met, such that the liquid can impact both the top and the bottom of the tank twice per single tank oscillation cycle. This observation is important because it provides additional support to the idea that the lumped liquid behavior is the determinant for the amount of energy that is dissipated following the vertical interaction with the tank. Specifically, the kinematic condition is related to the initial velocity that must be imparted to the liquid and causing it to enter a ballistic trajectory inside the tank such that two impacts with the tank per one cycle are possible. Importantly, the fact that this type of model is capable to predict the EC trends to a good degree is indicative of the fact that, at large fluid numbers, it is not the liquid-specific behavior that explains the sloshing-induced energy dissipation. The same numerical data can be used to show how the tank vertical acceleration varies with tank amplitude and frequency when EC is maximized. The major assumption of this model is that there is a steady-state harmonic tank motion. It does not take into account transient effects, even though similar conclusions may still be applied to R1 transient cases where the vertical flow develops rapidly. For example, having in mind the T-beam system discussed earlier, this graph here indicates that the vertical acceleration for which a system vibrating at approximately 10 Hz maximizes the induced damping effect is 3.5 Gs. This value corresponds very well with the experimentally observed damping saturation point shown earlier. To sum up, 3 vertical EMMs were investigated in this thesis, each with their own advantages and disadvantages, emphasizing different aspects of the vertical sloshing interaction. In what follows, I am going to present the last part of the thesis, which was concerned with an applied, more complex study. Going back to the structure of my work, the final step in understanding the complex vertical violent sloshing phenomena in aircraft wing tanks is to study a multi-degree of freedom scaled wing model. The setup is called MiniWatt, or Mini Wing of Tomorrow, and it represents a scaled research wing prototype whose structure and fuel tank was Froude scaled such that it correctly represents the dissipative energy due to sloshing in a scaled way. The scaled structure setup is shown here. It is approximately 3 meters long and consists of an underlying structure with 2 spars and 5 torque tubes cantilevered to a strong wall, which is shown here in blue. The main feature is the scaled fuel tank spanning a considerable length of the model, which had to be placed on top of the structure in order to be able to observe the sloshing patterns. 2 loading points, one at the leading edge and one at the trailing edge, are used to load the structure down and release it. Following the release event, the structure vibrates freely and its response is measured using accelerometers distributed across the model as shown here underneath. One accelerometer at the tip of the tank is used for the current work. 2 high frame rate video cameras are used as well to observe the liquid inside the tank from top and lateral. I'm going to present multiple sets of tests, such as the case with 50% filling level where the baffled tank is filled to 50% capacity with water, and the equivalent dry mass distribution case where the liquid is replaced with its frozen equivalent. Multiple parametric studies were conducted though, where the filling level was investigated as well as the initial amplitude, baffle design, and dihedral angle. Let us start by looking at the acceleration at the tip of the tank versus time for the 2 cases. Note that the time values are normalized to the period of the first bending mode. Each test was repeated 3 times, and mean values of accelerations are shown here, together with the red and green bands indicating minimum and maximum acceleration values. Following the step release event, the motion decays freely and the response is multimodal, as multiple frequency components are excited. As time progresses, each frequency component is damped at different rates, as can be seen in the insets here. This also shows that immediately after the release event, the wet structure has significantly lower acceleration amplitudes, indicating important additional damping effects. These acceleration signals can be unpacked into their frequency components and studied comparatively. A nonlinear least squares approach was used for the transient system identification, and today I'm not going to delve into the details of it, as this single discussion in itself can be quite lengthy, but rather jump directly to the results. Here you can see a representation of the dominant structural vibration modes that were used for the identification of the dry system. This is an amplitude-frequency characteristic of the dry signal shown previously, and note that because the system is nonlinear and the frequency is not constant in time, we make the distinction between uppercase f, which corresponds to the natural frequency of the system, and lowercase f, which is the frequency of the time-varying component. There are 4 dominant normal modes: the first and second out-of-plane bending mode, the first torsional mode, and a higher frequency bending mode, and you can see the corresponding shapes shown here on the upper side. The FFT of the reconstructed signal using the nonlinear least squares procedure is shown here in green as well, and there is a very good match between it and the original system, indicating that all features of the system are correctly captured. For this presentation, I will only focus on the first out-of-plane bending frequency component, as this one was found to be most affected by fuel sloshing. Moving on to fuel sloshing results, here we see the first component's amplitude versus normalized time for the dry and wet cases, with mean values and error bars showing the variability between 3 test repetitions. We see that the amplitude drops much faster for the wet case, indicative of substantial additional damping when the tank is partially filled. Focusing on the first part of the transient immediately after the step release at A, we can see in the inset that the amplitude is lower in the wet case, starting with the second half of the first period of motion. Here we also see a video from the side of the tank for the wet case, where the inner root section of the tank is on the right-hand side and the tip is to the left-hand side. In the first half period of motion, the liquid does not impact the top of the tank, and consequently, the amplitudes are similar in the 2 cases. Starting with the second half of the cycle, the liquid starts hitting the tank at the tip of the wing, and the amplitude of the first frequency component starts dropping immediately. This then continues afterwards as the flow develops into violent vertical sloshing in multiple tank cells. Here we also see the normalized frequency and damping ratio versus amplitude, again for the dry and wet cases. It is interesting to note that the error bars are larger in the wet case, indicative of less repeatability due to the chaotic nature of liquid motion. These graphs should be read from right to left if we have the time variable in mind, since the maximum amplitude is reached at the release point A. The frequency trends are similar between the wet and dry cases, increasing as the amplitude drops, likely caused by nonlinearities in the dry damping due to friction effects at the root. Substantial nonlinearity is seen especially in the damping shown here on the lower side. The dry structure damping comes mostly from the root and joints of the structure, whilst the wet case shows substantial additional damping due to the liquid action. I also marked the point B, showing the point where in the wet case shown here, the damping versus amplitude changes its variation from approximately constant in the AB region to constantly declining afterwards. Studying what the liquid does in the AB region, we see that the sloshing regime is dominated by vertical violent motion, which then starts to decrease in amplitude depending on the local spanwise position. This phenomenon, in turn, is consistent with previous findings in simpler vertical single degree of freedom sloshing experiments shown here on the left-hand side. We have already seen earlier that depending on the violence of the vertical sloshing, the damping value shows different trends. At the highest amplitudes, we have found that it reaches a plateau and it actually decreases afterwards, while at lower amplitudes it increases linearly depending on the amount of interaction with the ceiling of the tank. We observe the same trends here, where initially there is violent, turbulent vertical liquid motion, which then decays into lower amplitude sloshing, while still dissipating substantial amounts of energy out of the system. In the wing case, additional complexity is added by the span-wise acceleration effects, dry damping, and tank geometry. And this last point brings me to an example seen here, where even though the local acceleration is virtually the same in these two indicated neighboring cells, the sloshing patterns are very different due to the differences in local geometry. This suggests that the shape of the tank can be altered in order to promote significantly more liquid motion and consequently induce damping effects. As a side note, this similarity across scales that I just indicated can also be leveraged to formulate reduced order models. A finite element representation of the scale structure can be coupled with the sloshing force response surface of the single degree of freedom results in order to include the effect of liquid sloshing in more complex simulations. This approach gave very good initial results, which can be found in this reference shown here, and for which I will not go into details in this presentation. Moving forward, there are also other effects that were observed based on various parameters that were modified. Multiple experiments were conducted at various initial amplitudes of the step release. The damping and frequency versus amplitude trends are shown for 4 of such tests. Because it takes time for the sloshing flow to develop, and this time differs from one amplitude to the next, the nonlinear damping trends which are induced by the sloshing motion also differ. Depending on the initial amplitude, the damping values start from close to the dry case, and then, when the sloshing motion is fully developed, they converge to the same values. It is interesting to note that the frequency values are largely unaffected, confirming that the fuel motions are not the main driver, in these cases, of the frequency dependency on amplitude. Finally, it is worth taking a look at the most realistic case that I considered, the case with positive dihedral and baffles with scaled geometry. Multiple experiments were performed at filling levels between 10 and 90% with 10% increments, and snapshots of the developed flow after 7 periods of motion are shown on the left-hand side. On the right-hand side, I show the damping ratio and frequency characteristics in different forms for all filling levels. There are substantial differences between filling levels, and the maximum sloshing-induced damping was obtained in the 40 to 60% fill range. We can correlate these trends with the sloshing active cells, meaning the tank cells where any sloshing happens at all, and also with the sloshing active fraction, meaning the fraction of the liquid volume which is moving for each filling level. For instance, in the 90% fill case, we can see on the left-hand side that cells 1 to 4 are completely filled with liquid due to the dihedral, and no liquid movement was observed there at all, whilst only about 40% of the volume of liquid is active and sloshes. From a dynamics point of view, the completely filled cells act as dry mass, still modifying the wing frequencies, but with no effect on damping. The table on the right-hand side shows that the fraction of the mass which contributes to energy dissipation changes its span-wise location with filling level, shown via the active cells, and also that the active liquid fraction also varies with filling level. There is thus an interplay between the amount of liquid inside the tank, the amount inside each cell, and also the span-wise placement of the active cells, that all of these factors determine the nonlinear damping trends and the maximum values that are achieved. This concludes the overview of the thesis, and much more details can of course be found in the manuscript. The work presented in this thesis improves the understanding of nonlinear dynamic interaction between aircraft wings and the fuel contained inside their built-in tanks. The objectives formulated at the beginning of the work were met, and the following overall conclusions may be drawn. Multiple fundamental approaches were taken to the problem of vertical sloshing in order to address the research objectives, isolating the vertical component of the wing dynamic response due to gusts via multiple single degree of freedom investigations. The effect of vertical violent liquid sloshing on the transient single degree of freedom liquid structure coupled system was studied using the T-beam experimental campaign, which was shown in chapter 3, where a rectangular tank containing a variable amount of liquid was placed on an elastic element and released from a deformed position. The sloshing-induced damping ratio in vertical sloshing systems was demonstrated to be dependent on the filling level, the maximum amount of damping being achieved at 50% fill. Depending on the amplitude of excitation, 3 piecewise linear regimes were noted and correlated with the liquid motions. Further research into the fundamentals of vertical sloshing was conducted via 2 experimental campaigns that used harmonic excitation at set frequencies and amplitudes, investigating separately the different vertical sloshing regimes. Sloshing force information was available at the tank actuator interface, and the displacement, velocity, and acceleration of the tank were measured or derived. This measured information, together with sloshing pattern analysis based on high frame rate video footage, provided comprehensive experimental characterization of the dynamics and kinematics of the sloshing system. Particular focus was placed on the high amplitude regimes typical of aircraft gust encounters, where the dimensional energy dissipation was found to follow parabolic trends that were explained by the phasing between the liquid and the tank motions, as observed in the hysteresis cycles and subcycle formations. The experimental observations obtained here are significant as they provide a comprehensive characterization of the vertical sloshing-induced damping effects for an extensive amplitude and frequency of excitation range. Motivated by the ever-present need of fast numerical models, 3 sloshing equivalent mechanical models were proposed based on the extensive single degree of freedom experimental sloshing research, and each offering important insights into aspects of the vertical sloshing damping. The model formulations varied and were based on the coefficient of restitution, nonlinear spring damper elements, or ballistic harmonic collisions. All experimentally observed features were modeled using these EMMs, indicating the power of such numerical tools for computations of vertical violent sloshing. Building upon the extensive fundamental understanding of the single degree of freedom vertical sloshing, a novel sloshing wing model was designed and built in order to address the research objectives. The rig featured a semi-transparent fuel tank with a removable top lid and baffles, as well as the capacity of varying multiple parameters, such as the dihedral angle. The sloshing system was analyzed under step-release excitation that mimics the gust excitation experienced by a fixed wing in flight. The main findings have shown that the sloshing action causes substantial energy dissipation effects in the wing model, with amplitude characteristics that showed similarities to the vertical single degree of freedom cases. The damping of the first out-of-plane bending component was most affected by sloshing, with most damping effects noted in the 40 to 60% filling level range. Overall, the span-wise location of the liquid was the biggest determinant in the sloshing-induced damping, since the vertical acceleration and sloshing force moment arm depends strongly on the span-wise coordinate. Thinking about future work that needs to be done on this subject, there are multiple possible lines. From an experimental point of view, in this work the focus was placed on the vertical component of the sloshing motion, as it is dominant in the wing out-of-plane bending motions. For the wing model researched here, no significant sloshing effects were found in the other types of wing motions, such as in torsion. Supplementary lines of work could, however, prove fruitful in the coupling of heave and pitch tank motions. Such studies will be relevant especially for aeroelastic flutter-related investigations, where the bending and torsional coupling is important. This last observation also leads to the idea of completing the aeroelastic picture with the inclusion of the aerodynamic component, which would be meaningful for the study of the fuel sloshing effects on wing-integrated fuel tanks under in-flight conditions. From a more fundamental point of view, it was shown that there is a substantial increase in the sloshing dissipative energy when impacts with the ceiling and bottom of the tank occur. Further research could be conducted into the possibility of tailoring the tank geometry to promote such impacts and passively encourage supplementary energy dissipation. Strategic modifications of wing fuel tank geometry at certain span-wise locations without affecting the components essential for fuel system functions or the structural integrity of the wing may contribute to the passive increase of the net structural damping and improve the aircraft response to gusts. From a numerical perspective, whilst substantial progress was made in the modeling of vertical sloshing, additional work is needed at all levels of fidelity. The equivalent mechanical models discussed in this work showed success in modeling aspects of the vertical sloshing-induced damping in single-degree freedom system, but a numerical model that captures the full extent of the liquid structure interaction as manifested by the experimentally measured hysteresis cycles is still needed. To conclude, the experimental work and numerical modeling of vertical sloshing are important for passive gust loads alleviation. Sloshing-induced damping remains an active research topic, strongly motivated by industrial needs, especially with computationally inexpensive tools being highly relevant for the design and optimization of aircraft structures. Finally, a list with some of the author's relevant literature deriving from the work I presented here. Thank you.